In a previous video, I described what tensors are and how to do contraction and represent those contractions using Einstein notation. That video talked about what those terms mean. In this video, I will attempt to describe why I am interested in those three things and why I think they are so useful. In short, the answer is derivatives, specifically complex in the hard-to-handle sense, not the with imaginary numbers in it sense, derivatives. So let's start by describing when tensors are used to describe derivatives. This plot shows a function, the cube root of x, and its derivative. For a given value of x, the derivative tells us what the slope of f of x is with respect to a change in x. And because x is a scalar and f of x is a scalar, then the derivative of f of x with respect to x is also a scalar. But what if we have two different functions of x? We can put these two functions into a vector, and we can also compute the derivative of each of these functions with respect to x. In this case, x is a scalar, but f of x is a vector. This means that the derivative of f of x with respect to x is also going to be a vector. But what happens when x itself is a vector? This plot shows a scalar function, the z-axis in this plot is the f of x, that is a function of a vector x. The vector contains the scalars x and y. The derivative at any point on this surface can be computed, yielding a 2D vector giving us the direction of steepest descent or ascent. In this case, x is a vector, while f of x is a scalar, which means the derivative of f of x with respect to x is also a vector. So let's start a table where the columns are what dimensionality f of x is, and the rows are the dimensionality of x. Once again, a dimensionality of 0 means a scalar. So when x and f of x are both scalars, we have the case where the derivative of x with respect to x is also a scalar. If we make f of x a vector but keep x a scalar, then the derivative is a vector. Similarly, if x is a vector but f of x is a scalar, then the derivative of f of x is a vector. Now, if you are familiar with tensors, you may be starting to see a pattern and the role that tensors have to play with derivatives. If you have 1D tensors, commonly called vectors, for both f of x and x, then you will have a 2D tensor derivative of f of x with respect to x. Typically, this is just called a Jacobian matrix, but with tensors we don't have to limit ourselves to vectors on the input and output. Instead, we can expand this table to include any dimension of tensors for both f of x and x. If x is a 1D tensor or vector, and f of x is a 2D tensor or matrix, then we can store the derivative of f of x with respect to x in a 3D tensor. And to store the derivative of any tensor with respect to any other tensor, we simply need a tensor of a dimensionality that is the sum of the two input tensors' dimensionalities. Now, tensors are not strictly necessary here. You can take any tensor and vectorize it so it looks like a vector. But rather than taking a matrix or 3D tensor, or whatever object you're using, and forcing it to become a vector, we can just store the derivatives in a tensor format, and I find that notation to be much simpler. So that is the first reason why tensors are so useful when trying to do derivatives. But to truly understand the power of tensors when working with derivatives, we also need to review the chain rule of derivatives. Consider this simple expression. I have a scalar function, h of x, which is actually a compound function of both g of x and an f of two values, an f function of two values, labeled u and v. To compute the derivative of h of x with respect to x, we first compute the derivative of f with respect to both u and v. We also compute the derivatives of both u and v with respect to x. Given both of these derivatives, we can combine them together to get the derivative of h of x with respect to x using the chain rule. Note how the chain rule is just a summation across all matching partial derivatives. If we wanted to be more systematic, we could rewrite the chain rule as a summation across all intermediate variables. In this case, it is just u and v, but if there were more intermediate variables, we would sum across all of them. Furthermore, and the really cool part, is that this summation is essentially a dot product, and a dot product is also the basis of tensor contraction. So, not only can tensors store high-dimensional derivatives in a more intuitive format, tensor contractions can be used to combine partial derivatives to obtain the final derivative. Let's consider an example where I believe tensors really shine. This formula is used to model the imaging process, or how a camera takes images of the world. If I know the location of points in the world, the x variables, This formula helps me determine where they will show up in the image. In this formula, I subtract off the location of the camera, which is the t variable, to determine where the points are in relationship to the camera. Changing t leads to a change in the vectors from the camera to the world points. Associated with the camera is also an imaging plane that lies on the z-axis of the camera. Where the rays intersect the imaging plane determines where objects show up in the image. If the imaging plane rotates about the camera location, however, then the image points will change as well. To finish the projection process, we use a projection matrix, the K-matrix, that essentially represents the focal length of the camera, and then perform a projection operation, represented by the d function, that divides all vectors by the third elements of that vector. This division means that things which are further away will be closer to the center of the image than things that are close. So the point here is not to understand this projection equation per se, but to understand how we can take derivatives of this function with respect to r. But not really to the matrix r. The matrix r can be difficult to understand, but we may want to take the derivative with respect to a roll, pitch, and yaw representation of the rotation. This derivative can be very helpful if I want to determine what the roll, pitch, and yaw of the camera are, for example. How do we do this? Well, first, we express r as a function of roll, which is represented by phi, pitch, which is represented by theta, and yaw, which is represented by psi. We can then take the derivative of this representation with respect to roll, pitch, and yaw, or phi, theta, and yaw. Now, because you have the derivative of a matrix r with respect to a vector, the vector that has roll, pitch, and yaw in it, we can form a 3D tensor with the resulting derivatives. So, now let's go back to our original equation. To get the complete derivative, we also need to compute the partial derivatives of the d function with respect to the intermediate variables. This can be represented as a 2D tensor. Now that we have all these derivatives, we can write out the complete derivative function using the tensor notation as shown. Note that because tensor contractions properly represent the chain rule, the expression shown correctly computes the derivative of the whole equation. And if you are not convinced of the beauty of this representation, let me show you two more things using this same basic expression. First, this tensor representation can be very concisely represented in Python. By listing out the indices assigned to each tensor, and then listing which tensors you desire to operate on, the entire equation can be computed in one line of code. Second, consider the case where I want to compute the derivative with multiple world points. The current equation shows the derivative for just one point, but what if I want to compute the derivative for multiple points, once again with respect to roll, pitch, and yaw? The formula basically stays the same, but I add another index that goes across all the points, in this case the k-index. For different values of x, the index has to be added, but I also have to add the index to the d derivative because the derivatives have to be evaluated at a particular point. So there will be a different d matrix for every k. Once you have formed these tensors though, basically you can use the same line of code with just a couple of small modifications to compute the final derivative tensor. To review, why do we care about using tensors and tensor contraction and the Einstein notation? For me, the reason why I care is because the derivative of tensors with respect to other tensors can be represented in high-dimensional tensors, and also the tensor contraction can be used to implement the chain rule. Combining these two properties together enables a very concise notation when computing and using derivatives over high-dimensional objects. So I hope that you find the tensor notation as helpful as I have for computing complex derivatives.